Welcome to the fourth lecture of mathematical finance, and this week we are going to be talking about numerical methods for European options, and we are going to be covering material in chapter 7 of the book of Yoshi, but I'm going to also do a little bit extra material because the book of Yoshi is not completely up to date with the latest in numerical methods. So the main theme that I'm going to be talking about is that when we are computing the prices of derivatives, this is all about evaluating conditional expectations under some probability measure. And in the last weeks, you have mainly worked with the binomial tree. You did some numeraire change in the binomial tree. And now we're going to generalize this idea of evaluating expectations or evaluating martingales with a wider set of numerical tools that you can work with. So what we talked about last week is that the payoff of any asset divided by the numeraire will be a martingale process under the martingale measure Qn that belongs to that choice of numeraire. And if we denote this relative payoff as a function or a random variable fx subscript t, so we are looking at a payoff at time capital T, then this payoff is driven by some underlying random process, which could be the stock price or the logarithm of the stock price, or maybe the martingale, the stock price divided by the numeraire. So here I'm going to be looking fairly general at just taking an expectation of a random variable, and then towards the end I'm going to connect it back to kind of the Black-Scholes economy that we have been working with. So if I am computing a martingale expectation of a certain payoff, f at time capital T, as a function of a driving random variable or a collection of random variables, x, which I observe at time capital T, then the value today at time small t is just this expected value conditional on the information at time small t. And in general, I can express such an expectation as the integral from -infinity to infinity for all possible values of x of the payoff times the probability density function of f. And I'm using a little bit of special notation. So phi is what is known as the transition density, which as if my process at time small t is at value x small t, what's then the probability density of moving to every possible value x capital T at time capital T? So taking an expectation is the same as integrating the random variable x capital T with respect to the transition density phi from small t, from x small t to x large t. And this probability density function follows from the stochastic differential equation of the process x, but in general we don't know, and only for some very special cases do we explicitly know what the probability density function is of a specific stochastic process. So for the Black-Scholes model we know it. So basically when these mu and sigmas are constants or very simple functions of the underlying process x, can we then explicitly evaluate the density phi? And therefore we're going to be exploring different type of numerical methods which can be used depending on how explicitly we know the transition density phi, and maybe how complex the payoff function f as a function of x of t is. The three calculation approaches I'm going to be talking about is, first of all, is the direct kind of integration of the expectation. Basically the Black-Scholes formula, we actually do a closed form integration. And something else which is quite powerful but is not very well covered in the book of Yoshi is this idea of using Fourier transforms or characteristic functions, which is also basically a numerical integration of the expectation. Then a second class of methods are so-called finite difference methods, where we basically start from a partial differential equation and then use a numerical method to solve numerically the partial differential equation. And basically the binomial tree you have been working with, we can interpret this as a very specific example of a finite difference method, but there are more ways to discretize or compute these finite difference methods on the partial differential equation. And the third group of numerical methods is known as Monte Carlo simulation. And this is kind of the most direct way to implement this, because you directly start from the stochastic differential equation of the process. Then you draw random paths from that stochastic differential equation directly. And then at the end of every path, you say, I now have a realized value of my random variable. I can substitute that in my payoff function. And then if I do 10,000 or 100,000 or 1,000,000 paths, I can then approximate, or I can estimate the average of all those outcomes as an approximation of my martingale expectation. Now let's start with the first block, and this is this direct integration or numerical integration of the expectation. So most direct approach is to just say we do an analytical evaluation of this integral, where I use a little bit of shorthand notation. I know my payoff as a function of a random variable x of t, x at capital T. I know the transition density to go from the current value x small t to some future value x big T, and I just evaluate this integral in closed form. This is very rare that you can do this explicitly. And the Black and Scholes model with European option prices is an example, but as you have seen, even those calculations are not completely trivial. So there already you have to kind of use some tools out of your toolbox to kind of do this integral explicitly. Another approach is to just say I switch on my computer and I just do this integral numerically. So I use a numerical integration routine to integrate this integrand f times 5 for all values of x capital T, and I just do this integral numerically. This is a very powerful method, and it works very well if we have an explicit expression for the probability density function. And again, we don't, there are not for all models do we have explicit expressions. But if we have an explicit expression available, then numerical integration is a powerful and very accurate method of evaluating these expectations. However, numerical integration suffers from what's known as the curse of dimensionality. It works very well in doing a 1 or a 2 or a 3-dimensional integral, but the numerical complexity or the number of function evaluations you have to do explodes quite quickly. Because if you're doing this integral in 2 or 3 dimensions, you basically have to kind of fill either a square of evaluations or a cube of evaluations. So the number of function evaluations basically explodes very quickly for if you have nested integrals in multiple dimensions. Because basically for each dimension, you have to redo your numerical integration. For a large class of models, we do not know the probability density function phi itself in closed form, but we kind of know its cousin in closed form, and that is the characteristic function. What was the characteristic function? It's closely related to the moment generating function, but the moment generating function does not always exist, but the characteristic function does always exist. And it's like the expectation of a random variable capital X, but then evaluated. So I take e to the power of the random variable, and then I multiply it with this imaginary argument I times xi. And taking e to the power I xi of a certain function, this is known as computing the Fourier transform of the probability density function. And it turns out there is a fairly large class of models, which we'll talk about later. So this is mainly when we work with stochastic interest rates or with stochastic volatilities, where we can compute these Fourier transforms or these characteristic functions. We can compute these in closed form for the model. And then one possible way of kind of extracting then the probability density function is via inverting the Fourier transform. And one of the properties of the Fourier transform, it's almost a symmetric operation. So if I integrate over e to the power plus I xi x, I get the Fourier transform. And if I integrate over e to the power minus I xi x of phi star of xi, I get the original function phi of x back, but there is this factor 1 over 2 pi. And there are slightly different conventions. Physicists like to work with something that's completely symmetrical. So then you do a 1 over square root pi here, and then you have a 1 over square root pi over there. But let's say statisticians typically use this convention where they have no pi factors over here, but then they have to do a 1 over 2 pi over here. And of course, you have to take care of the plus I and the minus I in going forward, or going from the X space to the Fourier space and from the Fourier space back to the X space. However, if you want to evaluate this, typically you have to do numerical integration. And then extracting the density function directly via numerical integration for each point is numerically a very inefficient operation. And we're going to be looking at some tricks to do this computation faster, let's say directly in the Fourier space. There is a large class of models where we don't know the density function analytically, but we do know the characteristic function phi star analytically. And the notation that I'm using is I'm doing the Fourier transform on the payoff, so at x at time capital T, but the x of small t where I am today, I know that. So phi star is the conditional expectation, given that where I am today at time small t, of the random variable x capital T at some future date t. And this is a function phi star with arguments xi and x small t. And as I said earlier, examples of those models are stochastic interest rate models and stochastic volatility models, which we're going to be covering later in the course in chapter 14 and chapter 16. Now, if we want to calculate a payoff, and if we know the Fourier transform of the payoff random, of the payoff function, so this is then f star of xi. So after I take the Fourier transform, I replace an x capital T with this xi variable. Then I can do the following trick. I can start with my normal integration. So I want to integrate f of t x capital T against phi x capital T. And to do that, I could then invert for every point, invert the f star of xi. I'm basically directly using this formula over here, but now the f star Fourier transform. So the Fourier transform of the payoff. I now have a double integral. And now the trick that I can do is I can interchange the order of integration. So here in this integral, in the outer integral, I am integrating over x capital T. And in the inner integral, I'm integrating over xi. And if I switch the order of integration, then in the outer integral, I'm now integrating over xi. And then I'm bringing the integration over x capital T to the inner integral. And I basically put outside of the parentheses the integrand that does not depend on the variable that I'm integrating over. So now I can rewrite this integral. Instead of doing a Fourier inversion of f star, I am doing a Fourier integral of phi, but with kind of the non-standard argument minus I xi x of capital T. But this function we know because this is the characteristic function, but now evaluated in the argument minus xi. So this is a nice way of doing it. So if we have a characteristic function phi star, instead of doing this double integral, I can express the expectation of this martingale, or I can express this expectation of this payoff as a one-dimensional integration in the Fourier space, so using f star of psi and phi star in the argument of minus psi. And this is a very nice trick because I have now reduced my double integral to a single integral, or in the other way, in other words, I can do this integral as this is an expectation which I do directly in X space, which is a one-dimensional integral in X space. If I know the Fourier transform of the density, I can basically do a similar type of integral by basically integrating the Fourier transform of the payoff against the characteristic function. So this is a nice symmetry that we have, is that I can compute an expectation either in X space or in my Fourier space psi. So let's take a look at an example, because this is kind of an unusual way of thinking about expectations and doing integrations. So if I have a Brownian motion, then this has a normal distribution. So W, the Brownian motion at time capital T, is a normal variable with mean W small t and with variance T minus T. And we know the characteristic function for a normal density explicitly. It's e to the power I psi times the expectation. So that's e to the power I psi W small t. And then the variance term shows up as -1/2 psi squared, and then the variance T minus T. So we do see the structure that the characteristic function is a function of psi and the current value W small t, and we have this explicit, let's say, exponential form in W and in psi. So let's consider a Black and Scholes-Kohl option, and I have set R equal to 0, just to keep the formula slightly simpler. And then the payoff function as a function of the underlying stochastic process Wt, and note that I'm not using the stock price here as my stochastic process, but I'm using the Brownian motion directly as my underlying stochastic process, is the maximum of S capital T, and S capital T is S0 times e to the power -1/2 sigma squared T plus sigma Wt minus k, 0. And the question is now, can we compute the Fourier transform of this payoff? And then there is a problem, because the Fourier transform basically is only well defined for functions that are bounded, or for functions that, if you go to infinity, basically have to go to 0. And of course, this function, if W becomes larger and larger and larger, e to the power sigma square root of t basically explodes exponentially to plus infinity. So this is an unbounded function, and the Fourier transform of this payoff does not exist. So what is a clever trick? And this is a paper by two authors, Peter Carr and Dilip Madan, which was published in 1999. And I've added this paper as extra reading material on Canvas, is to basically tilt or twist the payoff by saying, I'm going to use at the payoff function, and I pre-multiply this with an extra factor e to the power -alpha Wt. Now, if alpha is larger than sigma, then the -alpha Wt kind of makes sure that this exploding tail of e to the power plus sigma is kind of compensated with this e to the power -alpha Wt term. So now I get a function that is of this form. So it looks a little bit like discounting, but of course I am using e to the power -alpha Wt to make sure that this function does not explode to infinity if W goes to infinity. So now we have kind of made this tilted payoff. But now the question is, how can I now compute the actual payoff that I want? Well, I have incorporated an e to the power -alpha Wt in the payoff. So therefore, I can do a trick that I can twist or shift my characteristic function to include an extra factor e to the power plus alpha wt. And how does this work? That I'm saying, if I consider the characteristic function e to the power minus ixi wt times e to the power plus alpha wt, I can bring these exponentials together and remember that I times I is -1. So I times minus I is +1. So I can kind of split this e to the power minus ixi w plus alpha w as e to the power, and then within parentheses minus xi and minus I alpha. And I am now evaluating a characteristic function. I am taking e to the power I times some argument times wt, and therefore this extra plus alpha wt I can kind of create, or I can deal with, by shifting the argument in my characteristic function from minus xi to minus xi times minus I alpha. If I now do this trick, then for alpha larger than sigma, I can explicitly and in closed form, or I can analytically compute the Fourier transform of this payoff. It's like taking an expectation against a exponentially distributed, but of course with complex values. But your let's say the normal integration tricks work. You just keep carrying that extra imaginary variable I around. So again, I am integrating from W bar to infinity, where W bar is that magical value for which the call option, or the tilted call option, becomes at the money. And then if I integrate from W bar to infinity, then I can basically do this integral and I get this function here. This looks a little bit complicated, but not too much. But you see that I have an explicit expression now for this integral, and this is now the Fourier transform because it is a function of xi. This is the Fourier transform of this tilted option payoff. And I can now say I want to compute, I can compute the option price as 1/2 pi times the integral of f alpha star as a function of xi times my characteristic function phi star as a function of xi. And if I integrate over all values of xi, this will give me the correct option value. And if you work with a little bit sophisticated numerical language like Scilab or MATLAB, and probably R as well, you can work directly with these complex numbers. And you can do this integral directly by integrating these functions with complex arguments numerically. And this function alpha, or this parameter alpha that you have here, does not influence the final outcome. So mathematically speaking, it doesn't matter which value of alpha that I choose for any value of alpha, because this alpha here is kind of compensated by that value of alpha over there. So mathematically, the choice of alpha is irrelevant as long as I choose a value of alpha strictly larger than sigma. But then it turns out that if you are a little bit clever and make a good choice for alpha, this greatly improves the numerical stability of this integral that you are evaluating numerically. Now, it's probably been a while since you've done complex numbers and integrating in the complex plane. So here I have given you a snippet of Scilab code. And it shows that maybe it's a bit scary to look at these complex formulas, but the nice thing about a kind of a modern mathematical computing language is you can quite literally take those complex formulas and basically program them directly into your language. So here I am doing the characteristic function of the Brownian motion. I have used a slightly different convention. So the Greek letter xi that I have here, I have called this consistently OM from omega in my code here. So the characteristic function is e to the power I times omega times x minus 1/2 omega squared t minus t. So I'm literally taking that formula from a few slides back. Then I am literally taking the formula for this twisted Fourier transform of the call option. And I have literally taken this formula that you see over here, and it's basically literally programmed here. It's minus s times e to the power minus 1/2 sigma squared t plus I times omega plus sigma minus a times the lower bound, w low. So it's quite nice. You can quite literally take the option price here. And here I've done another simplification. You see that I'm just evaluating an at the money option here. So my strike K here is just equal to S again. And then when I'm doing this integral, I need to integrate over F alpha star and phi star. So I am integrating over the real part of this Brownian motion characteristic function and the call tilde function evaluated in this argument here. And you see that I'm evaluating the Brownian motion characteristic function in the argument minus omega minus I times A, which is exactly this argument here. And then the code in Scilab is very simple, because you can basically say, I want to integrate from the lower value of psi to the higher value of psi. I've been quite sloppy here. I don't even bother about integrating from minus infinity to plus infinity. I'm just saying I'm taking a very small value of omega and a very high value. So I'm just integrating from minus 10 to plus 10 of this integral. And then Scilab does the numerical integration for me. And the answer is, you see this here is the output. I'm computing an at the money call option for a 1-year option with a current stock price of 100 and a strike price of 100. And then the Black-Scholes option formula gives me 9.946745. And the put option, because this is an at the money, is exactly the same value. And the numerical integration answer, that's the FTC, gives me also exactly the same answer, 9.947645. I think this is pretty cool, because what we are integrating over is we are doing this integral of these Fourier transforms of the payoff and of the density function or the characteristic function. And we are doing an integral with complex number. We are fishing out the real part of that. And the numerical value of that integral is, well, up to 7 significant digits, is exactly the same as the Black-Scholes formula or the normal expectation that you would normally compute. To give you a bit more feeling, this is this integral that you have here of the f star alpha times the phi star. And this real part of this integral I have basically plotted here for different values of alpha between -4 and +4. And then what you see is that for different values of alpha, although the numerical value or the mathematical outcome of the integral should be exactly the same, if we choose, let's say, not an optimal value of alpha, you get this behavior that the function you are integrating over is looking a little bit like a cosine function, which is kind of falling away, and you get this positive part, negative part, positive part, negative part, positive part, negative part. And this is what's causing a little bit of numerical trouble. It's not so difficult, but if you're making a very poor choice of alpha, you will get this very oscillating function that is only dying away to 0 very slowly. And then you're getting this plus and minus and plus and minus and plus and minus and plus and minus that all have to be integrated out quite accurately numerically to get the right value. However, for the optimal value of alpha, or the good value of alpha, this green function doesn't have this up, down, up, down, up, down behavior. So this is a much nicer function to integrate over numerically, because I don't have all these pluses and minuses that are canceling against each other. How do I find the best value for alpha? It turns out that it's not so hard. You can just simply put psi equal to 0. So you can look at this value here. And then you're going to say for different values of alpha, I want to minimize this value here, because it turns out if you minimize this value at 0, you are kind of, you are obtaining the smoothest possible function of this integrand that you want. And for different values of alpha, this middle point is larger. And then you get this kind of compensation with plus, minus, plus, minus, plus, minus. So in this graph here, I have basically taken this top point here at xi equal to 0, and I am tracking this for 3 different values of alpha, sorry, for all different values of alpha. And then you see that around alpha is 1.5 for this particular payoff. This is kind of the best possible choice to do your numerical integration. You also see that you don't have to find alpha with 12 significant digits if your choice of alpha is roughly right. So for a fairly wide range of alphas, let's say any value between 1/2 and 3, or maybe 4 and 5, is probably a good enough choice for alpha for this particular case. So it is, let's say, useful to kind of make a good choice of alpha, but it's not super important to find the absolute minimum here. You basically want to avoid being either in this tail here or, let's say, in that tail over here. And that's basically the values I've chosen here. So if sigma is 0.25, then the red function is roughly around here. And the blue function is at 0.4, so that's quite high, so that you find this value near 70 that you see up here. So that is, and the last thing that you sometimes see, and I think Kar and Madan have this formula as well, this function that you have here, the real part of this integral, is a so-called odd function. So this is perfectly symmetrical in the negative and the positive values. And this is kind of a property of a Fourier function. So you, for the numerical integration, you can also say, I basically do this integral from 0 to infinity. So I only take half this function and I'm just integrating over, let's say, the positive parts. But then, of course, I've taken only half of the function, so I have to multiply this by 2. And then you often see a Fourier inversion integral where you just say, I take 1 over pi, and then the integral from 0 to infinity. And that is, you can then exploit the symmetry that you have in this integrand here. In my numerical code here, I didn't bother about that. I'm just integrating root floors from -10 to +10. And again, the -10 is not a constant. That's, of course, a number that should be sufficiently large, such that this Fourier transform, that the integrand that I'm integrating over has really converged to 0 sufficiently. Okay, that was the part about the Fourier inversion and numerical integration of the integral. I now want to cover a second class of numerical methods, which are known as finite difference methods. The finite difference method basically starts with the partial differential equation. So that takes the partial differential equation as a central focus point. So the Black and Scholes partial differential equation for call option, we talked about this 2 or 3 weeks ago, is the time derivative plus r times s times the derivative in the s direction plus 1/2 sigma squared s squared times the second derivative in the s direction minus rc should be equal to 0, where c is the call option price, which is a function of small t and the stock price s. And in the general case, when we have more general stochastic processes and when we are looking at more complicated models with stochastic interest rates or stochastic volatility, this partial differential equation is like this parabolic partial differential equation where you have a time derivative and a first derivative in the x direction and a second derivative in the x direction and some discounting term. And when interest rate stochastics, then this is also a function of the underlying stochastic process x. So in the general case, I am kind of solving in general a partial differential equation of the form of a time derivative plus some drift times the first derivative in the x direction plus some diffusion term times the second derivative minus some discounting term. And the way we're going to solve such a partial differential equation numerically is by considering finite difference approximations of the partial derivatives of the function f of t of x. So the way that this works is that you say, start with a grid where we just do a fixed spacing of delta t and delta x values. So I have this kind of square grid or this matrix of values. And there I'm going to say each node on the grid, I'm going to keep track of a function value fij on this discrete node in the grid ij. And of course, this corresponds to the function value with argument I times delta t and j times delta x. And when I am, I've made this box here where I've kind of kept track of 6 nodes in the neighborhood of the function fij that I'm interested in. So if I go one step in this direction, my I goes from I to I plus 1. And if I go one level up, I go from j to j plus 1. And if I go one level down, I go from j to j minus 1. And I can approximate my time derivative, a partial derivative in the time direction, by saying it's f in the argument I plus 1 minus fi divided by delta t. So this is the finite difference approximation of the first derivative in the time direction. And the same thing, the first derivative in the x direction is I evaluate the function f in the point j plus 1 and the point j minus 1, and I subtract these two values. But if I go from j plus 1 to j minus 1, I have had 2 delta x's, so I have to divide by 2 delta x in the denominator. And my second derivative, if you remember that from your numerical analysis course, the second derivative can be evaluated by taking f in the point j plus 1 minus 2 times f in the point j plus f times evaluated in the point j minus 1, and I have to divide that by delta x squared. So these are the finite difference approximations of the time derivative, the x derivative, and the second derivative in the x direction. And as you may have noticed or may not have noticed, but what I have done here is I am evaluating the x derivatives not at I, but at I plus 1. So I'm kind of sitting in the node fij, and I'm kind of looking ahead at fi plus 1, j plus 1, fi plus 1j, and fi plus 1j minus 1. And this is known as doing explicit finite differences, because when I'm moving backwards in time, because I start at the end, because there I know the payoff, and then I'm kind of numerically walking backwards in time, the fi plus 1 values I already know, and then I'm taking a step back towards the fi value that I want to know. And now we're going to do something very simple. I say I have these finite difference approximations of my derivatives, and I am basically going to substitute these finite difference approximations into this partial differential equation. And then I have a set of linear expressions in the f's, because these finite difference approximations are linear functions of f, and I can basically collect all like terms together, and then it turns out that I can substitute the finite difference together and solve for the fij, that is the value one time step earlier that I would like to know, and I can express this as 1 over 1 plus r delta t times a big term of fi plus 1 j plus 1 plus a second term of fi plus 1j and a third term times I plus 1j minus 1. So this is kind of what I denote with the arrows here, is that the fij is a linear combination of the fi plus 1j plus 1, the fi plus 1j, and the fi plus 1j minus 1. Now let's take a look at these 3 red numbers here. If I am adding these 3 red numbers together, then the minus sigma squared and the plus 1/2 sigma squared and the plus 1/2 sigma squared cancel against each other. and the plus mu and the minus mu also cancel against each other. So these three red numbers all sum to 1. This sounds familiar, hopefully coming from the binomial tree, because these three red numbers are three numbers that sum to 1. And if I make sure that I choose my spacing delta t and delta x in such a way that all these three numbers are positive numbers, I can interpret these three numbers, which I now, as a shorthand notation, call PU, PM, and PD. These numbers are three probabilities because there are three positive numbers that add to 1. And of course, the 1 divided by 1 plus r delta t also may look familiar to you, because this is like the finite difference or the first order Taylor approximation, or the finite difference approximation of e to the power minus r delta t. So this is a discounting term. So in the trinomial tree, although I did not put anywhere a probabilistic interpretation or whatnot, I simply substituted this finite difference approximation into this partial differential equation, and I was collecting terms together. The explicit finite difference algorithm that comes out, we can give that the interpretation of doing a discounted expectation, because I'm taking PU times the payoff in the up state plus PM times the payoff in the middle state, and P down times the payoff in the down state. And if you make the choice that delta x is equal to sigma times square root of delta t, then this middle term basically becomes equal to 0. And I am just computing a P up times this value and a P down times that value. And the interpretation of the P up and the P down and the size of the delta x is basically very close to what you do in a binomial tree, where u times s, or the logarithm of u, u was e to the power plus sigma square root of delta t. And here I have, if you take a log transform, then you get a logarithm of the step size is sigma times square root of delta t. So we see this very nice connection. But in an explicit finite difference method, you are not forced to take this delta x and delta t choice. You can use this kind of three probability type of approximation. So the explicit finite difference method is kind of very easy to implement, and also kind of easy to understand, because you are explicitly taking this up, middle, down expectation. But the explicit finite difference method only converges if all these three numbers are positive numbers, it can be interpreted as three probabilities. And the main constraint is that delta x squared should be larger than sigma squared delta t. So the x spacing should be large enough relative to the delta t spacing. And that means if I want to evaluate a payoff with small delta x steps, then I am forced to take very small time steps delta t as well. And in the binomial tree, you are kind of automatically doing this by coupling the delta x and the square root delta t basically 1 to 1 together. There is, however, an alternative numerical method, and this is known as implicit finite difference. So what does implicit finite difference do? Is it says, well, here I evaluated the x derivatives at the time point I plus 1, but maybe it's more logical to evaluate, because I am in this node here, so I kind of want to look around where I am in the x direction. I can evaluate these derivatives at the I time point. If I do that, and again, I can do this trick and collect terms, I'm getting a different type of equation or connection, is that I'm saying the current value fi in node j plus 1, and the current value in fij, and the current value in fij minus 1 are connected with these three weights, but they don't have the interpretation of probabilities anymore, are connected via these three weights to the value fi plus 1j that I know from the previous iteration. So I can solve this, but now I say, and that's why it's called implicit finite difference, this is now a tri-diagonal system of equations, because the function Fij+1 kind of appears in the equation sitting above and below this. So I am solving a linear system of equations where if I take all these Fij values and stack them together in a vector, that for some matrix H, I'm taking the matrix H times Fi is equal to Fi+1. And then by solving this system of equations, I can then find out, or I can express Fi as a function of Fi+1. And the matrix H has a very clean form. It's a so-called tri-diagonal matrix. So I have these middle values, Hm on the middle diagonal, and I have these down values sitting on the upper diagonal, and I have these up values sitting on the down diagonal. And it turns out that you can solve numerically a tri-diagonal system of equations very efficiently via something called LU decomposition. And you should not be doing the matrix inverse of the matrix capital H, but use something like LU decomposition. And why is it useful to go through all this trouble? Is yes, you have to work a little bit harder to solve this system of equations, but the implicit finite difference method is nice in the sense that for whatever combination of delta t and delta x, so you can work with very large delta t's and very small delta x's, or work with very small delta t's, very small delta x's and very large delta t's, there is no constraint because the implicit finite difference method is always convergent, no matter what choice of delta t and delta x that you choose. I've been a little bit vague about stochastic process and partial differential equation. So the question is, what partial differential equation should we use as a basis for our finite difference methods? And the answer is you should choose the PDE that is most convenient to work with. So there are multiple ways of modeling the payoff as a function of an underlying stochastic process, X. And these different ways of choosing the underlying stochastic process and modeling the payoff leads to different forms of the partial differential equation. And if you implement it correctly, the partial differential equation with the appropriate boundary condition, you are computing the same price. You already saw Yoshi doing this in his book. When he was solving the Black and Scholes partial differential equation, he was kind of making different transformations to the problem by saying, I start with the standard Black and Scholes. So this is kind of the easiest one. And then the payoff is kind of directly the payoff that you are familiar with. But you can also say, what I also did with the Fourier transform a little bit, I basically don't want to model the stock price directly. I want to model the logarithm of the stock price. And applying Ito's lemma, I know explicitly what the partial differential equation is for the stock price. So then the partial differential equation becomes nicer to work with and is numerically better behaved because now I have constants over here and not kind of, let's say, state-dependent coefficients. So for solving PDEs, the trick is kind of find that transformation of the PDE that makes the coefficients in your PDE as constant as possible, because the closer they are to a constant, kind of the nicer they are to solve numerically. So if you take this log transform, you get these two constants here, but then of course your payoff has to be redefined as the maximum of e to the power xt. But you can also say, maybe I want to do, still are inspired by the case of last week, I want to do a log transform and model this as a martingale. So as your random variable, you could maybe choose the logarithm of s divided by b. Now, s divided by b is then a martingale, but taking a logarithm is a nonlinear transformation. So the x process, which is the logarithm of s over b, has minus 1/2 sigma squared plus sigma. So then I get the minus 1/2 sigma squared plus 1/2 sigma squared, so also constant coefficients. But because I'm modeling this as a martingale, I'm only taking an expectation. So I have no discounting anymore, and the discounting term disappears. So then I have this partial differential equation. But now the payoff, of course, has to be expressed in terms of s divided by b and k divided by b. And then I was modeling x as the logarithm of s over b, so that the s divided by b becomes e to the power x. All these three partial differential equations with the appropriate boundary conditions will lead to the same numerical value for the Black-Scholes call option price. But let's say the numerical behavior of the finite difference grid that you are using to solve each of these partial differential equations can be different. And in particular, if you choose partial differential equations with constants, with coefficients as close to a constant as possible, that will give you better numerical behavior for your numerical solution with the finite difference methods. Both the numerical integration methods and the finite difference method, they do suffer from what is known as the curse of dimensionality. So basically, both numerical integration and finite difference methods are only practical for problems with, let's say, 3 or 4 random variables that I'm trying to track in time. So the Black-Scholes is no problem. I have basically only one random variable. But if we move to more complicated options and more complicated models, I may want to track multiple stochastic processes at once. And then if I have a problem that I either with numerical integration or with my grid, I have 100 points that I'm tracking through time on my finite difference grid or in my numerical integral. Well, 100 points is no problem in one dimension. But if I scale this problem up to a 3-dimensional problem, I am basically taking 100 points in the x direction, 100 points in the y direction, 100 points in the z direction. So then I'm already tracking 100 to the third. That's 1 million points already. If I go to the 4th space dimension, I'm jumping up from 1 million points to 100 million points. So the number of evaluations and the number of grid points that you have to do basically explodes exponentially with the number of dimensions that you are tracking. So for practical implementations, numerical integration and finite difference methods work best for low dimensional problems with, let's say, 3 or 4 space dimensions at most. The last block that I'm going to be talking about is Monte Carlo simulation. Monte Carlo simulation has yet another starting point. Is with Monte Carlo simulation, you basically start directly from the stochastic differential equation. So suppose that my underlying driver follows the stochastic differential equation. dx is mu tx dd plus sigma tx dw. And the function mu and sigma can be whatever you want. This can be vector valued stochastic processes with vector valued Brownian motions. The nice thing about Monte Carlo simulation is if I know the stochastic differential equation, I am basically in business. Because how does Monte Carlo simulation work? It says I take the information from the stochastic differential equation and I basically directly translate this into a scheme for generating paths from this stochastic process. So this is kind of nice. So that's why I put a green smiley there. Is if I know the stochastic differential equation, I am in business because I can basically generate directly drawing paths from the stochastic differential equation. And once I have drawn paths for my stochastic process X, no matter how complicated or how horrendous mu and sigma are, if I then know a stochastic path for my process X, I can then basically say at the end at time capital T, I know where my process X is going to end. And I evaluate the payoff, and then if I have 10,000 or 100,000 paths, I basically average over all these outcomes. So how does this work? Simulating directly from the stochastic differential equation is you use something which is known as the Euler discretization. And the Euler discretization is very simple. You look in the differential equation, and everywhere you see a d, you are replacing this by a discrete delta. So delta x is the value from x at time point t plus delta t minus the current value xt. So this first dx becomes x at time point t plus delta t minus xt. This mu delta t becomes mu tx times delta t. And the sigma dw becomes sigma tx times delta w. Now this is an approximation. So I am making an approximation error of order delta t to the power 3/2. And this is this 3/2 term that you also saw in the derivation of Ito's lemma. So this is not an exact discretization, but if I make my time steps smaller and smaller and smaller, this Euler, the approximation of the true stochastic process becomes more and more and more accurate, and I'm roughly the error term is kind of falling with delta t to the power 3/2. So if I know that I am today in value x of small t, I can push forward to value t plus delta t. Mu tx is known at time small t, sigma tx is known at time small t. So the only random term that's coming in is this Brownian increment. And this Brownian increment is really nice to work with, because a Brownian increment, just following the definition, is a normal random variable with mean 0 and with variance delta t. And these Brownian increments, because I'm taking a step into the future, quote unquote, all these increments are IID from each other. And the increment from t to delta t is also independent from the xt process. So the way that you construct paths from a stochastic differential equation with an Euler discretization is you say the value in the next time step along this path is the value where I am today, xt, plus mu tx, and I can evaluate this because I know xt, times the length of the time step delta t, plus the sigma tx, which I also already know given x of small t, times a square root delta t, which is the standard deviation of the Brownian motion, times epsilon t. And this epsilon t is just a standard normal 0,1 IID random variable. And many computer software packages basically can directly generate IID distributed standard normal random variables. So the way that you start is you first generate a bunch of standard normal random variables. You start at your initial value x0, and then you basically push with time steps delta t, push your x process forward with time steps delta t, using these epsilon random variables to kind of generate a stochastic path. And for time steps smaller and smaller and smaller, the discrete delta t approximation of the path is converging to the true stochastic process if you make your time steps smaller and smaller and smaller. How do we now compute a payoff? Is again, I want to compute the expectation of a function of the random variable at time capital T. And the way that I do that is I'm generating m paths for this process with time steps delta t, ending at time capital T at the x capital T in path number small m. And given this numerical value of xt in path number m, I substitute this in the payoff, and I basically repeat, or I take the average over all the payoff for all the paths. And this gives me an approximation of the true expectation that I want to compute. Now, what makes Monte Carlo valuation extremely powerful is that, and the other methods cannot deal with that very well, but Monte Carlo can deal with it very cleanly, is for some products, you say, I am looking at the complete history of what happened in the past, and that will determine my payoff. So with a bit of abuse of notation, I can take the expectation of a function f depending on x capital T, but the function f is allowed to depend on all the x values that I have seen in the history of the past. So maybe it's a barrier option, or maybe for some insurance products, for the people who followed Life Insurance 1. If I have an insurance product that says I am getting some amount of profit sharing depending on the investment returns that the insurance company makes along the way, then the final value that I get at the end basically depends on the whole path of the economy that I have followed. With a Monte Carlo value, you can very easily deal with this. So the Monte Carlo value that I compute is an estimator of the mean. So the Monte Carlo value is kind of an estimator E hat, where I just take the average of all the payoffs for each path, xtm. And if the number of paths goes to infinity, I am converging to this true expectation. And another way of interpreting Monte Carlo, and that makes a connection back to the first, let's say, integration method, is to say by generating a bunch of paths, I am generating an empirical distribution function of this process X. And another way of looking at this summation is by saying I am integrating the payoff against the empirical distribution function of the discrete approximation with capital M number of paths of this process X. And again, this empirical distribution function converges to the true theoretical distribution function if the number of time steps becomes small enough and if the number of paths, capital M, becomes large enough. Why does Monte Carlo actually work? Well, it's a simple application of the strong law of large numbers. I am taking the average of independent draws from this stochastic process. So each realized payoff value f subscript m is an IID draw, is an independent draw from this random variable fm, and I'm taking the average of that as the sum of these values. And I know from the law of large numbers that even if I scale this up with the square root of m, that the average E hat estimator is converging to the true value. And I have even this asymptotic normality result. So if I blow this up by square root of m, then I am converging asymptotically to a normal distribution with the true mean. And the variance of the estimator is equal to the variance of the payoff that I'm trying to compute. And in a finite sample, I can approximate these asymptotic. I can use the asymptotic normal distribution to kind of make an approximation of the probability distribution of my estimator E hat. And I then know that this guy is unbiased. It's a normal distribution with the correct mean. And the variance of the estimator is the variance of the payoff that I'm trying to estimate divided by the number of paths, or the standard error is the standard deviation of the payoff divided by the square root of the number of paths. So let's say what's the Achilles heel, but also the powerful point of Monte Carlo is that it always converges with 1 over square root of m type of convergence, and it does not depend on the dimension of the problem. So Monte Carlo does not suffer from the curse of dimensionality. So 1 over square root of m convergence is fairly slow, but for high dimensional problems, I'm also getting this 1 over square root of m, and basically for high dimensional problems where the numerical integration and the finite difference method simply explode by the number of possible nodes or function evaluations that you have to make. And for high dimensional path dependent type of payoffs, a Monte Carlo simulation is kind of the best algorithm that we have, even though it has a relatively slow convergence of 1 over square root of m. That's it for this week, and I am going to stop the recording